Hello everyone. The title of my poster is a heuristic approach to compute service request resolution time. This poster is a brief summary of the work I did as a research intern at the IBM research lab in Almaden. I worked with the cloud services analytics team. I was very lucky to have been mentored by Taiga Nakamura, Pawan Chowdhary, Shubhi Asthana, Ali Megahead, and Bing Zhang. I thank them all for their continued guidance and support. The business context for this project is a process called a quote to cash or Q2C. In enterprise companies, there is a separate staff called the sales support staff dedicated to selling products and services to potential clients and customers. Since large companies can have thousands of products and product portfolios, it may not be possible for the sales support staff to know all the details of all the products and services while they are talking to potential clients. These details could be about pricing, features, availability of products, and so on. In these cases, the sales support staff might need help in the sales negotiations, and the way to do this is to seek the missing details or information from non-customer facing backend teams. The volume of the negotiations being carried out is very high, and the need for help is consistent. So these backend teams and the sales support staff need an effective, streamlined way of communication. A common way to achieve this is through tickets. The sales support staff will create tickets stating the details needed to be known from the backend team and send it to one of the backend teams. Once the backend team gets a ticket, it is assigned to one of the employees in the team who works to resolve the ticket. When the employee gets back to the sales support staff with the necessary answers, the ticket is said to have been resolved. For example, at IBM, a ticket is called a service request or an SR. When the sales support staff is working with the customers to sell IBM services, they often request the Q2C support and open a new SR with the backend teams. These backend teams are called as squads. These SRs are often characterized by features such as the geography, the market or business subdivision they occur in, the sales stage they signify in a sales negotiation, the size and the business value of the accompanying sale. The SR resolution time varies because of features such as the SR complexity, employee skills, employee availability, SR volume, and other features like the market, business subdivision, and engagement option. Stakeholders at different stages in this process would benefit from knowing answers to questions they have around resolution times of SRs, such as future capacity or cycle time trends, to make wiser business decisions around squad utilization and capacity optimization. For this reason, computing the time required to solve future SRs becomes an important problem statement. More formally, the goal of this project is, given the complexity and volume of SRs and the several features that characterize an SR, how can we predict the average resolution time for a given SR type? And of course, at the outset, there are several questions one has to address before formulating a potential solution, such as, at what level should we predict the SR resolution time? Should it be at the squad level, market level, or tribe level? Which features would be the most useful for this task? Would a monthly prediction be more accurate than a weekly prediction? Should we predict for the long term or for the short term? Along these lines, the goal of this poster is to delineate a method to solve the problem of forecasting the weekly time taken on an average to resolve the SRs assigned to employees. This solution is a part of a larger problem statement around staffing recommendation. The prediction of an average resolution time can be used with the forecast of SR volume to compute the average squad capacity, which in turn can be used for squad workload optimization. We propose an interoperable solution based on the weighted moving averages method, which has the following steps. The first step involves feature engineering, where we select the right set of features to segment our data and use it further for our task. This involves addressing the challenge of having many features and their underlying hierarchy. All of these together determine SR resolution times. Now, more features means more information, which can always be good, but this can also lead to more data sparsity after segmentation. We choose features to segment our data such that we try different combinations of features and select the ones which give a good balance between data sparsity, information granularity, and business intuition. The next step involves data pre-processing. We choose 2 rolling quarters of the past as a historical data to build our model on. We clean the data by removing invalid rows, such as the ones with negative SR times, and perform outlier substitution. Note that this is different from outlier removal. We substitute those SR times lower or higher than the 3 standard deviations for the SR time with the values at the 3rd standard deviation. This not only helps us preserve the data size of our data subset, but also helps us reduce the effect of outliers. With the clean data with us now, we can segment it on the tribe, sub-brand, and engagement option features, which denote the market, business subdivision, and the pre or post-sale stage of the SRs respectively. The third step involves performing analytics on the segmented data. We group each data subset to get the average volume of SRs per week and the average SR time per week. In doing so, we deal with insufficient data in 2 ways. For missing volumes, we use interpolation and replace the missing volumes with its nearest neighbor volumes. On the other hand, we replace missing weekly average squat times with the quarterly average squat time. The prediction is then done on this processed data using the weighted moving averages algorithm, where volume is used as the weight. For a given horizon, the forecast for the first week in the horizon is a result of the weighted moving averages. But the forecast for the rest of the weeks is done by recursively taking a simple moving average of the predicted values over a suitable rolling window. The evaluation of the forecast is done using the MAPE or the mean absolute percentage error. To decide what window size to use for which data subset, we use the concept of a dynamic rolling window, where we perform the predictions over a range of window sizes and choose the one which gives the lowest MAPE. This drastically improves our average accuracy over the entire dataset. In the context of our problem, a MAPE of less than 20% is desirable, and we are able to successfully achieve that for more than 75% of our combinations or data subset. This means that more than 80% accuracy for more than 228,000 SRs. This prediction model has been incorporated to the Cognitive Score Insights project or the CSI project at IBM Research and is being accessed by the Q2C team. The proposed solution is beneficial in terms of its interoperability in that it can be used for predictions with contexts analogous to a problem statement. In terms of business impact, the proposed solution was approved by the stakeholders and will be actively used in production. The solution will also find itself to be a part of a patent which has been approved for filing. The patent is based on the idea of employee reskilling and improving resource optimization. A future path could be the exploration of regression techniques which involve using volume as a regressor and performing transformations on the data such as the Box-Cox transformation. The preliminary results using the open source library Prophet look very promising. Thank you.